In this example problem, we have a solid ball of radius r sub b that has a uniform charge density ρ. And the questions we're going to attempt to answer are, what is the magnitude of the electric field at a distance of r greater than r sub b from the center of the ball? And then also, what is the magnitude of the electric field at a distance r less than r sub b from the center of the ball? So to start solving this problem, let's first address this thing ρ. So this is going to be the charge density, that is the charge on the ball over the entire volume. So we can rewrite this and say that the total charge on the ball is equal to ρ times the volume of the ball. We plug in for volume of a sphere, that's 4/3 pi r cubed. We have a relationship between the charge density ρ, the radius of the ball r sub b, and that will give us the charge on the ball. To address the first part of this problem, what's the magnitude of the electric field at a distance outside of the center of the ball? For this part, since the radius that we're interested in is larger than r sub b, we can use a surface that's outside of the ball. So if here's my ball with the radius r sub b, I can pick a surface somewhere out here with radius r to evaluate. Since there is charge inside of this ball, I know that the electric field is non-zero, so the electric flux is going to be equal to the charge enclosed over epsilon naught, which is also, again, the other part of Gauss's law, is the integral over the entire surface of the electric field dotted with the area vector. Because this has spherical symmetry, I can immediately say that the area vector and the electric field vector are pointing the same direction, so I don't have to worry about angles in this case. Because my surface is entirely outside of the sphere and I've centered the sphere at it, I could basically treat the sphere as a point charge. So I know that my electric field is also going to be uniform. Evaluating this integral, I have a nice symmetry where I have the magnitude of the electric field times the surface area of a sphere. Now, Q enclosed, we already calculated in terms of ρ, the radius r sub b. So I can plug those values in here on the other side, and I can solve for what the electric field is. Making some simplifications here, I can cancel my pi, and I can cancel a 4 on each side. So this leaves me with ρ r sub b cubed, because that's due to the volume, over 3 epsilon naught r squared, where again r is the distance from the center of the ball out to wherever we're evaluating this electric field. So here is our answer for part A. In part B, we'll draw our ball a little bit bigger. Again, the ball has radius r sub b, but we're going to be evaluating it at some smaller radius. So the dashed line there, again, represents the surface that I'm going to evaluate this over. This time, my charge enclosed is going to be less because I'm not including the total charge. But since the ratio of charge to volume remains the same, ρ is still a constant. So as we've done with other problems, ρ is equal to the charge enclosed over, we'll say, the volume enclosed. The volume enclosed then is just going to be 4/3 pi r cubed. Whereas in part A we used r sub b, the radius of the entire ball. Now we're using some smaller radius, so we need just regular r there, because we're going to be missing some parts. We're not going to be getting everything, all the stuff that's out here on the outer edges between there. The evaluation of my integral, however, is going to be the exact same. So on the right hand side, I still have a uniform field. It still depends on how far out I am. My portion of the surface area is exactly the same. Again, the surface area of the sphere, closed surface that I'm evaluating here, still depends on how large it is. So the only thing that's different now is what Q enclosed is. For part A, Q enclosed was the total charge the ball has. For part B, Q enclosed is only going to be the portion of the charge that makes up that smaller portion of the ball. So we have our formula for Q enclosed as it relates to ρ and r cubed up above. We just need to rewrite things a little bit. So I can solve my equation from above in terms of what my new Q enclosed is for this portion. So again, this comes from this equation. I can then plug this in to my equation for the electric field. I can make some cancellations here. Pi again, 4 again. And this time, you'll notice that it doesn't depend on RB at all. Since RB just sets the size of the sphere and we're inside that sphere, we're looking at a smaller portion of that sphere. I can cancel some of my R's here. And if I rewrite this, I find that the electric field depends only on the charge density, the radius at which I'm evaluating the electric field, and the constant that is the permittivity of free space. One thing to note when looking at these two results, if I want to know what the electric field at the very, very center of this ball is, since the radius at that point is 0, the electric field has to be 0. If I want to know what the electric field at a very, very large distance away, I would look at our result from part B. Since it's 1 over r squared, as r gets very large up to infinity, that makes the electric field 0 at that point as well. The distance away from the center of the ball, where the electric field happens to be the largest, is going to occur at the surface of the ball itself, where r equals r sub b. That will give us the largest field possible, which you can see when r equals r sub b, these two equations equal each other.